Here are the first set of notes for Chapter 2. And in this set of notes, we will be looking at distributions. So a distribution is a record, it's a record of variability. So let's unpack that a little bit. First of all, you've already looked at distributions. A distribution could simply be a list of numbers. Or you could take that list of numbers and organize it in something like a dot plot. Later, we'll also look at histograms and box plots. Then let's look at the word variability. Variability just means variation or changes. So we're in that list of numbers, we're going to see changes. We're going to see some numbers that are bigger and some numbers that are smaller. And we call that variability. We will describe a distribution with 3 attributes. These are so important. The first one is the center, the second one is the spread, and the third attribute is called the shape. So we'll be looking at those 3 things in depth today. And in particular, what we're going to look at today are the shapes that distributions can take. And we're going to start with the uniform or rectangular distribution. So this is a way that we can describe shape. So in a uniform or rectangular distribution, there is little change in the frequency over the distribution. Here's an example. The number of births per month in the United States in 1997 was approximately uniform, with about 325,000 births per month. Now I can make a sketch of this. On the y-axis, I'm going to put frequency. Frequency is the same thing as the number of births in a given month. And then on the horizontal axis, I'm going to put the month. And I'm going to abbreviate January, February, March, April, May, June, July, August, September, October, November, December. Then what we see here is that there are about 325,000 births per month. Isn't that crazy to think about that? That's more people than live in the city of Madison being born every month. So I'm going to put a scale here, 325,000. And then in a uniform distribution, what happens is, let me do that again. Each bar is approximately the same height. So the January bar and the February bar and the March bar, they're all roughly, I did it again. They're roughly the same height. In fact, I really could just sketch this by drawing a rectangle, because every month we have about 325,000 births, creating this rectangular shape. Okay, so that's one shape that we see sometimes, a uniform or rectangular distribution. Another shape that we see is the normal distribution. And the normal distribution is bell-shaped. If we go back to our data from activity 2.1, here we can see in our first set of data, and I've only got 4 data points here, but these 4 data points make a nice symmetrical shape, and we're going to see this shape over and over and over again. So I'm going to sketch this. I'm going to start with an x-axis, and then this is sometimes called the bell-shaped curve because it's kind of shaped like a bell. I'm going to try that one more time. You can practice on your paper while I try to get this right. Oh, it's hard to do on the iPad. There's a ridge that's getting in my way. Okay, well, that'll have to do. Okay, so there's our bell-shaped curve. It's supposed to be perfectly symmetrical. I did a mediocre job. Because it's perfectly symmetrical, it has what's called a line of symmetry. The line of symmetry also tells us where the mean or the average of the data is. Some other features. I'm drawing 2 dots here, which are called the inflection points. And inflection is like slope. And what we see here is we see the slope is changing. Here, the slope is concave up, meaning that the graph is curving up, like scooping up. And on the other side of that inflection point, it's concave down. There's actually some really sophisticated mathematics behind this that is outside the scope of this course, but you can kind of get the idea there. And then there's my inflection point. And the same thing happens on the other side. The other thing that's special, the reason we care about the inflection point, is the inflection point also defines for us where the standard deviation falls. So we're not going to define standard deviation quite yet, but it is a measure of spread. So the mean is the same thing as an average. Oops. And the mean tells us it's a measure of center. Standard deviation is a measure of spread. How spread out is the data, and we'll be looking at that later in this chapter. And then that inflection point is the point between concave up and concave down. And it also defines where that standard deviation is. So there are 3 places where we routinely see a normal distribution. One is variations in measurements, and we saw this in activity 2.1, where we measured the marbles. We can also see it in natural variations in populations and variations in averages of random samples. So these next 2 bullet points we're going to talk about later in the course. Okay, so we've looked now at 2 shapes. We've got the uniform or rectangular distribution as a shape. This shape is, again, just a shape that looks like a rectangle. We've got the normal distribution, which has got this bell shape to it. So anything that looks like this shape is approximately normal. And next we need to be able to describe some distributions that are not symmetrical. So the 2 shapes that are not symmetrical are skewed right and skewed left. In a skewed right distribution, there's a tail on the right. And in a distribution that is skewed on the left, there is a tail on the left, on the left side. Not fail. Tail. And if I go back to our data, our measuring diameters data, we can see, for example, here, this is skewed to the right. There's a tail. And this one is skewed to the left. There's a tail. So sometimes sketching on top of the picture can help us figure out what we're doing. Okay, back to the notes. So those are 2 skewed distributions, or 2 names of skewed distributions. And again, that's a way to describe the shape of a distribution. Here's an example on the next page. Here's a histogram for the income of a sample of 500 people from Columbia, Sauk, and Dodge counties in Wisconsin. The first thing that I notice is that if I sketch this, it's skewed to the right. And what they're asking us to do here is to report the quartiles of the distribution. So the quartiles divides the data into quarters. Now in this data, there's 500 people, and if I take 500 people and divide by 4, I get 125. And it's really interesting here because it turns out, I'm going to get rid of this, the first 500 people, the first 125 people actually fall in this first rectangle. So there's about 170 people in that rectangle. So that is our first quartile, because the 125th person falls in that rectangle. So the first quartile is 0, meaning that 25% of the people make $0 or less. Okay, next I'm going to look at the median, or the 50th percentile. The 50th percentile is going to fall at the 250th person. So again, the first quarter was 125 people. If I double that to find the middle, that would be at the 250th person. So if I add up these bars, so I'm going to have to zoom in here. The first one was 170. This one is about 30. This one is about 50. If I add up 170 and 30 and 50, it turns out that the median is right about here. That's 20,000. So this is about, I don't know, 8,000 maybe. And that is where half the people, if I were to shade in all of this area, half the area would be below this blue line, and the other half, if I added up all these little rectangles, would be above that blue line. So the median is at about $8,000 a year. This is old data, by the way. If I were going to find the third quartile, then I would have to count up another 250 people. So let's see. So this one's 50 people. This one's, I'm going to round to make this go a little faster. This one looks like it's almost 20. This one's 30, 40, 30. What am I at here? 100, 170. Let's see. 20, that's 190. I'm going to round this one. 20, that's 210. 10, 220. So somewhere around here, if I add up all these red numbers, I get 250 more people, and it looks like they make about $37,000, or this line is at $37,000. So if I, again, look at this area, that shaded area now represents 75% of the people make less than $37,000, and then the rest of the people, if I add up all of these, this is 25% of the people make more than $37,000. So to sum up, I figured out that my lower quartile value was $8,000. The median was roughly $20,000. No, I'm sorry. Let me back up here. The lower quartile was 0. The median was $8,000, and the upper quartile was $37,000. Okay, we're going to look at one more shape. Our last shape is called bimodal. And in a bimodal distribution, we have 2 peaks or modes. So a mode is a peak. So if I like to kind of take a highlighter and smooth out the graph and see what that looks like. And so I see two peaks here. And when I look at this data, this is a histogram representing the life expectancies of women in world countries. And what I see with this bimodal distribution is it represents, well, this is also old data from the 90s, and things have changed a bit. But here I've got a cluster of countries where women live to be about 50 years old. And here I've got another cluster of countries where women live to be almost 80 years old. And this could be due to a whole bunch of things, but I have a feeling it has to do with money and healthcare. Okay, so other features of the gap, or of graphs. These are other shape features. One is outliers. And if I go back up here, if I look at these folks here, those are outliers on this graph. There's two people that make over $100,000. So outliers are separated, from the rest of the data. And they're separated by a gap. So a gap is just a space in the data. So going back to this graph, these are outliers, and I could call this a gap. And then a cluster is just a clump of data, or data that's bunched together. All right, that covers our first lesson on shapes. To review, the different shapes were uniform or rectangular, normal, skewed left and right. We practiced finding quartiles by breaking the data into 4 equal sections. And then bimodal was another shape. And finally, we have 3 features: outliers, gaps, and clusters that we can use to describe graphs.